Hello, welcome to another module in this massive open online course. So far we are looking at source coding and we have looked at different kinds of codes, and we said that we are interested in the design of uniquely decodable codes and in particular prefix free or instantaneous codes. Alright, so we are interested in design of prefix free or instantaneous codes which form a subset of uniquely decodable codes. Okay, now let us look at a new concept coding of course in the design and as well as the decoding of such prefix free codes, and this is the binary tree representation of a code. Okay, so in this module we would like to start looking at a binary tree representation of a code and as I have told you, this is useful for design as well the design as well as decoding of codes. Okay, it's useful for the design as well as decoding of the codes. For instance, consider the code four symbol code S0 represented by 10, S1 represented by 00, S2 represented by 11 and S3 represented by 10. Okay. Now if you look at this code, I can represent it as a binary tree, and the binary tree representation would be as follows. If I construct a binary tree for this code, so I start with the root, then for 1 I go above, for 0 I go below. Okay, so for instance S0 is 0 followed by another 0, so this is S0. Now S1 would be, well, I am sorry, this is S1, S1 would be 0 followed by another 0. So now if I would like to do S0, S0 would be 1 followed by 0. So for 1 you go to the top of the tree, 1 you go the branch, take a branch going above and then followed by 0. So this is S0 and S2 is 1 1. So you go 1 and again take the branch above, that is 1. So this is S1 and S3 would be 1 1 0. So 1 1 and you take a further 0, that would be your S3. So S3 would be 1 1 0. So this is S1. So we have S1, S0. So we have represented the code using a binary tree. That is what you have done. We have simply represented the code using a binary tree. Okay, so this is a binary tree representation for the above code. Okay. Now if you can see in this code, you can see that S1, the code word S1 lies along, or I am sorry, this is the code word S2, S2 is 1 1, this is the code word S2. So, you can see that S2 lies along the path to S3, S2 lies along path to S2 lies along the path to, that is symbol 2 lies along the path to symbol 3, and you can see S2, this is 1 1, S3 is 1 1 0. So, therefore, S2 forms a prefix S2 forms a prefix of S3. Thus, we can see that S2 in this binary tree representation of the code, S2, the node S2 which represents the code word, which is represented by the code word 1 1, that lies along the path to the code word for S3, which is represented by 1 1 0. Therefore, this is not a prefix free code. Okay. So, therefore, this is not, you can see that it is not a prefix free code, because S2 forms of S2 lies along. So, in general, if any code word, right, if any code word lies along the path, that is, if any code word lies along the path another code word in the binary tree representation, then it is not a prefix, it is not a prefix free code, it is not a prefix free code if any code word lies along. So, from the binary tree representation, basically one can see if it is a prefix free code or not. For instance, consider another code. Okay. Consider now S0 represented by 1, S1 represented by 0 1, S2 represented by 0 0 1, and S3 represented by 0 0 0. Now, if you look at this code, you can see that, well, again let us look at the binary tree representation. You go above for 1, below for 0, S0 is 1. So, this is basically your S0, S1 is 0 comma 1, S1 is, you go below for 0, 0 comma 1, this is S1, and for S2 you have 0 0 1, so 0 0 goes below, S2 is 0 0 1, and S3 is 0 0 0. S3 is 0 0 0, and now if you can see, basically you can see that no symbol lies, or no code word for no, so the code word for any symbol. So, this is the binary tree. Code word for any symbol, right. So, all codes end on leaf nodes, all code words end on leaf nodes, these are known as, these are the various leaf nodes. All code words are on leaf nodes, and basically no code word is on the path of another. For instance, if you would like to go to S2, this is, well, let me just draw it. This is the path to S2. This is the path to S1, path to S0, path to S3. So, no code word is on the path of any other code word. Okay. And another way to say is no code word is an ancestor of another code word, right. So, our ancestor is basically where a node, and that node splits into further nodes in the binary tree. So, this node is said to be the ancestor node of the corresponding branches and the leaves that emanate from those branches. So, no code word is the ancestor of another code. For instance, here you can see in the previous one, S2 is the ancestor of S3, which is basically the same thing as saying S2 is a prefix of S3. S2 is an ancestor node of S3. However, here you have no code is an ancestor, no code word, all these are the same things. Okay, no code word is an ancestor node no code word is an ancestor node for another code word. Okay, and therefore no code word is an ancestor code for another code word. Therefore, this is a therefore, this is a prefix free code. So, in a binary tree for a prefix free code, well, no code word lies along the path to another code word, and no code word is basically an ancestor node to another code word. Okay, all the code words are along leaf nodes. Okay, which means the end nodes of any particular branch. Okay, they don't form intermediate nodes. Okay, so that is a binary tree. So, from a binary tree representation, one can see that if it's a one can check quickly if it's a prefix free node or prefix free code or not. Now, again, if you look again at the same code, let me draw the binary tree again. This is 1 as 0, this is 0, this is 1, this is S1, this is 0, 1, 0, S2, S3. Now, if you look at the depth of this tree, binary tree, the depth equals L max equals 3. Okay, so you have 0, 0. So, if depth is the maximum number, that is the maximum number, you can think of the depth of the binary. So, the binary tree L max is the length. So, here you can see L max equal to 3, that is you have a code word with 3 bits, that is the maximum number of bits in a code word is 3. So, the maximum length of the code word is 3, and you can see that the binary depth of the binary tree is also 3, that is the number of levels in the binary tree used for representing the code. number of levels in binary tree representation equal to 3. This is L max. L max is equal to maximum number of bits in code word. So, you can see that if you look at the code words, again if you go back, you have L0 equal to 1, this is the length 1 bit, L1 equal to 2 and L2 equal to 3, length of code word 2, length of code word 3 equal to 3. So, therefore, from this you can see that L max is equal to 3. Okay, so then it's very simple. So, the maximum of 3 bits are used to represent each code word. Okay, and that is the depth of the binary tree, that is the number of levels in this binary tree. Now, you will observe something interesting. If you go to S0, now let us look at, now it is not difficult to see that for a given binary tree, okay, now if you have a code word of S0, now because S0 terminates this leaf node, now the number of nodes that are eliminated, because the leaf node terminates at N0, this is at level 1, level L0 equal to 1, this is at level L0 equal to 1. Okay. Now, therefore, the number of terminated nodes now what happens is, because you are terminating this level 1 with S0, the corresponding number of nodes that are removed at level 3, okay. So, the number of nodes you can see here in this case, number of nodes eliminated at level 3 equals 2 to the raised to L max minus Li, that is basically in this case that is 2 raised to 3 minus 1 Li, that is I equal to 0. So, 2 raised to 3 Li equal to I equal to 0. So, L naught equal to 1, 2 raised to 3 minus 1, that is 2 raised to 2 equal to 4, and this is an interesting result. So, what you are observing is, because we are terminating, right, in this prefix free code, because we are terminating the node, the code at, because no other code word can lie further down from S0, right, for that matter along any code word, because then it would be a prefix, that it would not be a prefix free code. Okay. So, therefore, in order for it to be a prefix free code, you are terminating that particular branch at that code word S0, which means that further down at the depth of the binary tree, that is the L max, this leads to a removal from the binary tree of 2 to the power of L max minus Li. In this case 2 to the power of L max minus L naught. For the ith code word, it will lead to the removal of 2 to the power of L max minus Li in general. For instance, if you can look at S1, S1 is at level 1, I cannot draw this binary tree completely, but if you look at level 2, this is at level 2, correct, S1 is at level 2 because it has 2 bits 0 1. So, that will lead to the removal of 2 to the power of L max, that is 3, minus L1, that is 2, 2 to the power of 3 minus 2 nodes at depth L max. So, S1 2 to the power of 3 minus 2 equal to 2 nodes. Okay. Now, S2 and S3 are already at level 3, that is the depth. Okay, so S2 corresponds to one node, S3 corresponds to one node each, that is 2 to the power of L max, that is 3 minus 3 Li is also 3 bits, 2 to the power of 3 minus 3 0, that is one node, each node corresponds to one node at level. So what you see is each node in this binary tree corresponds to, that is if you extend it further to the depth of the binary tree, that is L max, corresponds to 2 to the power of L max minus Li distinct nodes. Now these nodes cannot overlap corresponding to the different code words, because remember it is a prefix free code, right. So no code lies along the path to another code word. Therefore each code word, so to summarize this, in the prefix free code, corresponds to 2 to the power of L max minus Li distinct code words at L max, at depth L max, or at depth of the binary tree, at depth L max now. From this we observe that summation, from this we observe that summation I equal to 0 m minus 1 2 to the power of L max minus Li must be less than or equal to, that is 2 to the power of L max. Since 2 to the power of L max is the maximum number of nodes possible at depth L max. For instance, if you look at L max equal to 3, correct, L max equal to 3, the maximum number of nodes equal to 2 to the power of 3 equal to 8. Okay. Since what you observe is, it is very simple, at depth L max the maximum number of nodes that are possible in this binary tree is 2 to the power of L max. Now in each node, in each code word, you are removing, or it corresponds to 2 to the power of L max minus Li distinct code words at the depth L max. Therefore the sum of all these nodes corresponding to these different code words, if you add the sum of all these nodes at the depth L max corresponding to all these code words, that must naturally be less than or equal to 2 to the power of L max, which is the maximum number of distinct nodes that is possible at the depth L max. And then from this we have a very simple result. We have, now rewriting this, summation I equal to 0 to m minus 1 2 to the power of L max minus Li less than or equal to 2 to the power of L max. This implies that you take 2 to the power of L max common, summation I equal to 0 to m minus 1 2 to the power of minus Li less than or equal to 2 to the power of L max. Now cancel 2 to the power of L max from both sides, and what you will get
is a very elegant inequality which says summation I equal to 0 to m minus 1 2 to the power of minus Li is less than or equal to 1, and this is a fundamental inequality that has to be obeyed by the prefix free code which we have derived from the binary tree, and this is termed as the Kraft inequality. This is termed as a Kraft inequality for a is the Kraft inequality for prefix, that is we are considering S0, S1, S2, Sm minus 1 with lengths L0, L1, L2 up to Lm minus 1. These are the corresponding lengths. These are the corresponding code word lengths. So, with these code word lengths, the Kraft inequality tells me for a prefix free code we have to satisfy I equal to 0 to m minus 1 2 to the power of minus Li less than or equal to 1. This is your Kraft inequality. Okay, this is the Kraft inequality. This is the Kraft inequality, and now interestingly the converse can also be shown to be true, and it naturally follows if you can look at the proof that if there are lengths L0, L1, Lm minus 1 which satisfy this Kraft inequality, then there exists a prefix free code for this alphabet with the given code word lengths. Okay, so let us note that also. Converse is also true. Which basically implies if lengths Li satisfy condition above, there exists a prefix free code there exists a prefix free code with code word length is equal to Li. So, that is what the Kraft inequality tells us. Okay. So, this module we have looked at a very important result, that is Kraft inequality based on a binary tree representation for a prefix free code. We said that the binary representation of a prefix free code is such that no code word is an ancestor code word, ancestor node for any other code word, alright. And using this property, looking at the total number of distinct nodes that are possible at the depth, maximum depth of the binary tree, that is at the level L max corresponding to the maximum length of the code word in any code, we have shown that this code word lengths Li must satisfy summation I equal to 0 to m minus 1 2 to the power of minus Li less than or equal to 1. This is termed as the Kraft inequality. And subsequently we will use the Kraft inequality to derive further insights about the nature of the code and principles regarding code construction. Alright, so we will stop here. Thank you very much.